Good morning, everyone. This is Mr. Couple. Today I'm joined with my IBHL Year 1 students. Say hello if you're on voice chat, please.
Hello.
Hello.
There we go. Thanks, guys. Today we'll be talking about standing waves. Standing waves are fundamental to understanding how musical instruments work, and they're the last topic that we'll be studying on waves. I'm not going to go over the main ideas at the beginning because they kind of are spoilers, so let's just get started. All right, what we want to start off is looking at the reflection of wave pulses at a boundary. So you imagine like you've got this wave pulse coming in and it hits this wall. This end of the rope is fixed, so it's like physically stuck and attached to the edge, whereas over here it's tied to a ring, and the ring is free to go up and down. I think we kind of messed around with this when we had the slinky out in the hallway, and like if we were still at school right now, I would have had you guys go recreate that same thing. I feel like I'm getting a lot of lag. I don't know. Anyway, okay. So what happens is if you have a fixed end, and you might remember having explored this, is that the wave pulse comes in, it hits the boundary, and when it bounces off, it gets inverted. Whereas if the end is free to move, and this I didn't get to show you guys, but if the end is free to move, it just comes back the same way that it came in. So there's no inversion. So we call this an inversion. All right, so the first thing that we need to understand in terms of understanding how standing waves are created is we need to understand the difference between a fixed end and an open end. The fixed end is going to end up a little bit later being called a node, and then the free to move end is going to be called an antinode. So I'll just throw those terms out there now so that a little bit later it'll make more sense. What we want to do is try to explain this inversion behavior. So let me show you guys this animation of it. So here comes the pulse, and it gets reflected back as an inversion. So we want to try to explain why this happens. And so the explanation that's typically given for this is just using Newton's third law. And so the way to think about it is, I don't know if you guys can see my mouse cursor, hopefully you can. When the wave hits the boundary right there, what's going to happen is the string is going to exert an upward force on the wall, and then the wall is going to exert, by Newton's third law, a downward force on the string. And since the string has way less mass than the wall, you're going to see a much larger effect of this force on the string, resulting in this downward pull on the string, which sends it and inverts it. And that's the basic understanding of that. All right, so does that make sense? You guys have questions about that?
I think the stream is like messed up or something.
I can't see the stream. I've just now noticed that.
Let's see.
It's like it's loading. That's all
Oh,
it's
is it?
saying. Yeah.
Then that means that our the server's having issues. I'm sorry, guys. I'm gonna keep recording. Hopefully it comes back. You can feel free to leave. But yeah, it sounds like our Discord just added video chatting, and they're probably like having server issues this morning with that. So I'm sorry it's not working out. But you can watch the video on YouTube. If it comes back in, feel free to join back. But I'd just say don't worry about it, guys. You can just leave. I'm just gonna keep going. Okay.
I'll just listen.
All right. Me too.
Okay. Cool. All right. So what we were talking about was how the wave comes in and then hits the. I just realized I heard a World of Warcraft alert in
How?
there.
I
Anyway,
really don't have alerts on.
I heard it. I heard the what is it called? What's that mod? Like it gives you the alerts during a boss fight. Anyway, I'm gonna stop. Okay. Focus. I got 25 minutes left. All right. So the basic idea was like we said that when the wave hits the boundary, it's going to get inverted, and we said it gets inverted because of Newton's third law, that the string exerts a force on the wall, and the wall exerts a force on the string. But since the wall was way heavier, it ended up having a greater effect, right? That's just F equals ma. When the mass is less, the acceleration is more. And since the mass of the string is way less than the wall, the string is going to have a greater acceleration. Now, you could see that what happens if the mass of the wall was less, and so that's what's going on when the end is free to move. So there's a ring there. The ring has a much lower mass, and so when the string exerts the force on the ring also accelerates equally to the string, and so you end up not having this inversion effect that occurs there. So that's the important thing is you get a node versus an antinode. All right, so next question is, what happens if instead of a pulse, we send a continuous wave? So what would happen if we send a continuous wave at the boundary. And so that's what this animation is going to show us. So we're going to have that inversion, and then the wave gets sent back. And so what we see happening now is it's forming this really interesting pattern, and this pattern is called a standing wave. Oh, I just lost it. So this pattern is called a standing wave. And so what's happening is the incoming wave and the reflected wave are interfering with each other and creating this pattern, which is called a standing wave. So notice how it's going up and down like that. So the incoming wave interferes with the outcoming reflected wave, and it creates this interference pattern where it looks like the wave is standing still. So I wanted to explore this a little bit more by going out to Desmos and showing you like I could recreate this inside Desmos using simple math. So what I'll do is I'll define a function that I'll just call sine of x plus b, or I think it's minus that I want. And so I'll add a slider b, and when I hit play, you can see that now this wave is like traveling. Well, I don't want it to come backwards. I just want it to keep going forward. So I'll click on this and just say keep going forward. Now when I do that, it's going to slow it down significantly. So I'll just also click to speed it up a bit. That's way too fast. 10 is probably pretty good. Okay, cool. And then I'm going to adjust my windows over here. Let's see. So the y-axis will go -3 to +3, and the x-axis will go 0 to +20. We don't need the negative space. All right, that looks pretty good. So there's my wave traveling to the right. Okay, then that's the incoming wave that's traveling towards the boundary. So now I want to do, pause. I want to do the reflected wave. So I'll call that g of x. So g of x, since it gets reflected, we're going to do like a hard boundary, like a fixed boundary. Then that means that I'm going to need to invert this. And it's traveling the opposite direction. So instead of shifting it to the left, to the right, with adding, like this is just an algebraic shift or transformation, I'm going to want to shift it the opposite direction. So if I turn this guy off and hit animate, now we can see that this wave is inverted of the other one, and it's moving the opposite direction. Okay, so now let's go into the options. And so what I'm going to do is make these guys different colors. So the incoming will make that blue, the reflected wave will make it red. And I'm going to make them kind of like dotted lines. And the reason I'm doing that is because they're not actually going to exist. What's really going to exist is a superposition of these two waves. And so this is the superposition of the two waves. So now we can see that when one wave is moving to the right, that's the blue wave, and then another part of that wave bounces off and reflects inverted, the superposition ends up being this purple wave here. Let me make it black. So now if I turn off the original two waves, this is all that we will see. We won't see the two waves. We won't see the incoming wave and the reflected wave. We're not going to see those. We're just going to see the superposition of those two waves, where we have these two things. And so what you notice is like there are parts of the wave where it stands still, and then there are other parts of the wave where you have these large variations in the displacement. And so, like we said before, these points here are called nodes, where it's fixed, and then these parts here are called antinodes, where it's free to move. All right, so I'm going to pause this. Here we go. And then I'll leave this up in case you want to come back to it. But I just thought that'd be really cool to show you guys how Desmos can be used to create a little quick animation of standing waves. All right, so what we found is a standing wave consists of a repeating pattern of nodes and antinodes. And so it might be interesting to know, why does this happen? So nodes, so these are the points where the wave seems to be standing, like not standing still. Obviously, the whole thing is a standing wave. It looks like the wave's not traveling. Like it looks like the wave is just stuck there. So if we go back to the animation again. So the wave appears to just be stuck. Like it's just moving up and down. It looks like it's not traveling. Whereas these waves, these are traveling waves, where the wave is actually physically moving through space. Whereas a standing wave looks like it's not going anywhere, that it's just getting bigger and smaller, but it's not moving. What we want to do is explain how the nodes form. So the nodes are points where, as a result of destructive interference, the displacement is always 0. So if we stare at this, let me bring these guys up again. So if we look at a node, which is right here, you'll notice that the blue wave and the red wave are always, at that point, they're always exactly opposite each other. So why don't we slow this down a bit And we can see that more clearly. So if we just look at this one point right there, you'll notice that the red wave is always above by the same amount that the blue wave is below. So they'll always be equal and opposite to each other at that point. And so it'll always be zero. The displacement will always be zero at that point. But if we look at the antinode, which is here, you'll notice that it cycles back and forth between them being both positive, like they are right now, and then now as they move apart from each other, they switch to both being zero, and then there you go. So you can see like as it's changing, like it's switching back and forth between them, lining up with each other and then getting really big, where they line up, versus them canceling out now. So we can see at this point right there we go to zero. So you can see like this at these two positions that they're either constructively interfering, which is what's happening at the antinode, constructive interference, the two waves are always on the same side, versus at the node where they're always on opposite sides of the equilibrium with that midpoint line. Let me pause it. Okay, so that's the two names that you need to know, the node and the antinode. All right, so down on this picture, we could label the nodes and the antinodes. This is generally how a standing wave is going to be illustrated. So these points here where there's no movement or where the wave sort of overlaps, those points are called the nodes. And then the antinodes are these other places here where there's this large variation in displacement. And so those points are called the antinodes. All right, there's this video I want to show you guys. This is Standing Waves on a String. It's by an old friend of mine, James Lincoln. He was working at the UCLA physics department when we made this video. It was about 10 years ago. I'm going to show you guys the video.
This is a device used to demonstrate standing waves. Now, despite the name, the waves are actually reflecting back and forth across the string. They're not standing at all. These fluorescent lights allow the string to glow so it's more visible in the dark. Here's the first standing wave, or fundamental mode. Notice that half of a wavelength is visible, or another way to say it is, twice of the rope's length is one wavelength. The second harmonic has a node in the middle, a place of zero movement, and two antinodes, places of large movement.
So what's kind of not clear here is that what's happening is you have one wave going this way, reflecting off, coming back, and then reflecting again, and this wave is bouncing back and forth, like it's always in here. But what happens is on one side you have this oscillator that's just oscillating, and it's sending a wave down, and then it's reflecting back again. So what happens is you actually end up getting a lot of different frequencies that can actually fit within this string. And so what he's going to do here in this video is just show you all the different frequencies that can fit within the string without canceling out with each other.
A full wavelength is represented. Now these antinodes are of such large movement that if you touched one, you would mess up the whole wave. This is the third harmonic. You'll notice there are now 3 antinodes, of course, and 2 nodes.
So we call this the third harmonic. So there's 3 antinodes and 2 nodes. And so in a minute, he's going to ask you a question to see if you can predict, if we go up to like certain number of harmonics, how many antinodes and nodes are going to be. So notice here that this is the third harmonic. There are 3 antinodes and there's 2 nodes.
You'll also notice that the wavelength is 2/3 of the total length. This is one full wavelength. The fourth harmonic shows 4 antinodes and 3 nodes. A strobe light reveals that 2 wavelengths are present in the length of the string. Now it's time for a test of what you've learned. For the fifth harmonic, what would the wavelength be?
All right, so if we have the fifth harmonic, then what we noticed the pattern was that the number of antinodes is always the same as the number of the harmonic, and the number of nodes is always 1 less. All right, well, anyway, we're going to stop the video there. I just thought it'd be useful for you guys to see the real life versions of them before we get all crazy. So the basic idea there is that different standing wave patterns can be established on the string as various frequencies. So like you can have all these different frequencies can fit within the string. Like because all you have to have is one end has to be, or I should say both ends have to be fixed. Well, there's a variety of waves that can have that property where the wavelength of the wave is exactly fitting into the string. These are called the harmonic frequencies. They're all like the different possible frequencies that you can fit on the string. Getting some weird feedback over here. Hey guys, I'm doing a check. Is the stream working yet?
Nope.
I can't see anything.
Let me see if I try and restart it up again. How about now?
Yeah,
I
it's
see
working
you.
now.
You guys can see it now?
Yeah.
Okay. Well, I don't really want to redo what I had already done, but I guess I can really quickly show you guys this video. So what happens is you've got this string here, and you're sending waves across this string, and it's creating what are called standing waves in the string. And so he's showing us
Antinodes are of such large movement that if you
he's showing us these different waves that can be formed inside the string. So this is called the third harmonic, where what's happening is the wave is coming in here, it's hitting the boundary, and it's bouncing back. This is the third harmonic. And then out here, this is the fifth harmonic. So there's 1, 2, 3, 4, 5 antinodes. And these points here where it doesn't move, those are called the nodes. So I can show you this animation. This is an animation I was talking about a little bit earlier that you guys couldn't see. So what we have here is we have a blue wave moving to the right. I can speed this up a little bit. So we have this blue wave is traveling to the right, and it's going to hit some boundary over here, and then it's going to reflect off. And that's what this wave is doing here. If we put both of them together, this can't exist in one medium, right? You can't be pulled in two different directions. You have to have a superposition. So the superposition of those two waves looks like this. What do you guys think? No, can't see it. So this is called a standing wave.
So it's basically two waves going, or it's like creating two waves using one wave?
Yeah, so this is the wave that was originally there. So there was a source that was oscillating on the string, and it sent a wave traveling this direction. Then it hits the edge and it bounces back. When it bounces back, it gets inverted. So let me pause it. So okay, so what you'll notice here is that it's kind of hard to see. Let's do it there. Okay, so you can see that the red wave and the blue wave are inversions of each other. And so that's what this minus sign right here is. That minus is saying, hey, whatever the other wave was, minus it. But if we travel through space, then you'll notice that they don't always stay exactly inverted of each other. Like sometimes they're exactly inverted, but other times they actually line up with each other. So when you look at the superposition of these two waves, you can see that it's going to oscillate back and forth between periods where there's maximal constructive interference where they line up, and then parts where they don't line up and they destructively interfere with each other. And so that creates these regions called nodes, which is where the wave doesn't move at all. Like the medium stands still. There's no displacement. And in other areas called antinodes where you have maximum displacement.
Then what's the neutral displacement where it's like flattened?
This here where it's completely flat, right there. I missed it.
Yeah.
That's where the waves are exactly canceling out with each other.
So there'd be no sound at that point?
Well, sound is always an oscillation. Like it's always going up and down. So there's always going to be a point where there's no pressure.
Okay.
All right, let's see. So what I was just talking about was that you can have different waves can fit within like if you have a string where there's two ends that are fixed, you can have different waves that fit within that string. The requirement is, in order to fit there, the requirement is that it has to have a node at either end, or I should say the ends are fixed. And so these are called the harmonic frequencies. So we're going to try to examine these more closely and get a better understanding of this. Okay, so we're going to look at two things. We're going to look at a visual, and we're going to look at like a mathematical representation. So we're going to draw the first four harmonics on a string with both ends fixed. So we know that this end has to be fixed and this end has to be fixed. So the pattern is it always goes, if we look at the picture up here, it always goes node, antinode, node, antinode, node, antinode. So it always has to rotate back and forth between nodes and antinodes. So down here, we know that if the two sides are fixed, then we're going to have an antinode in the center for this first one. So it's going to look like that, and then it's going to come back like that. So it'll be moving up and down between the two. So the wave is actually kind of like existing like within this, it's going up and down. The second harmonic would be, again, fixed on either end. But now instead of having one antinode, we'd have to have two antinodes. So there'd have to be an antinode here and an antinode here, meaning there'd be a node in the center. So the second harmonic looks like this. I'll just put those on there just for fun, and so on. And then if we keep going, the pattern is that however many, whatever the number of the harmonic is, that's what the n is, that you'll have that many antinodes. So the next one will have 3 antinodes. Did I do it? No, I messed up. Let's see, so there's going to be a node here, there's going to be a node here. I did not draw that perfectly, but it's okay. Should I fix it? I'm going to fix it because it's bad. Okay, here. Like that. And then the last one will be 4 antinodes. So it goes like that. All right, so what we want to do is we want to figure out what the wavelength of the wave is. So we're going to say that between the two ends of this, that's a distance called L. And so we want to say, how does the wavelength of the wave compare to that? Well, you can see this first wave, the full wavelength would be out to here. So the full wavelength of the wave would actually not just be 1L, because 1L only gets us halfway, right? There's the crest, but we also need the trough. So that means that for this first one, the wavelength of this wave that's fitting between these ends is 2L. So the first, man, I cannot get my lambda to look good. So the first wavelength is 2L. So I'm putting the subscript 1 there to say that this is the first harmonic. If we look at the second one, the wavelength is exactly fitting within the string. So the second harmonic, the wavelength is the length. Here the wavelength is, there's one full wavelength. Notice that if we divide up the string into 3 pieces, then this is represented, so the third wavelength is 2/3 of the length. So if we look at each of these as being 1/3 of the length, then we're filling 2/3 of the length. And then for the last one, there's our wavelength. You can clearly see that this is just half of the full length of the string. So what we want to do is we want to figure out some sort of pattern that's going on here, some sort of generic expression where we give the number, the 1, 2, 3, 4, we give the number of the harmonic and it tells us the wavelength. So if you look at this more closely, we could actually write this like, let's see. So what I want to do is write the number. So if I put, let's see, we're trying to figure out how we could express this a little bit differently. So I know that 2/2 is equal to 1. And I know here that if I have if I have 2/3, okay, and then if I put 2/1, and down here I can put 2/4. There we go. And so if we just realize that if we put a 2 on the top, then the number, so down here, this is our number. So the number of the harmonic that we want goes on the bottom. So that's the generic pattern. So we see that it's going to be 2L/n. That's what the wavelength of the nth harmonic is going to be. So I'll record that down here. So the wavelength of the nth harmonic is 2L/n. And so we can check that real quick. If n is equal to 2, then we would have lambda 2 would be 2L/2, which is L. So let's go check if the second wavelength was L. Yeah, second wavelength was L. So this will work. This will give you the wavelength of any harmonic that you want. Just pick a number and you can calculate the wavelength of that harmonic. What we want to do now is come up with an equation that tells us the frequency. Well, we have the wavelength. So how do we find the frequency? We just need to use that C is equal to wavelength times the frequency. So C being the speed of the wave. If we look at this, we notice that we already know what lambda is because we found it over there. So C is equal to 2L/n times the frequency. So if I just want to solve for the frequency, and this is the nth frequency, since this was the nth wavelength, this is the nth frequency. So if we solve that for the frequency, it's going to be n times the speed of the wave divided by 2 times L. Okay, now it says show that all harmonics are integer multiples of the first harmonic. Okay, so let's calculate F1. So this is called the fundamental frequency, or the fundamental mode is what James called it in his video, or the first harmonic. So if I calculate this, I'm going to get n is equal to 1. So the fundamental frequency is C over 2L. But then realize that this equation has C over 2L right there. So we can substitute. So we can say that Fn is going to equal to n times C over 2L, which is just F1. And so you get this equation that says, if you know the fundamental frequency, so like for instance, if I said the fundamental frequency was 250 hertz, then the second fundamental frequency would be double 250. So it would be 500. And then the third harmonic would be 250 times 3. So it would be 750. And then the fourth one would be another 250. So it'd be 1,000. And so this is allowing you to figure out the different frequencies that can be created or that can fit on the string. Okay, so now let's talk about music. So this relates very strongly to music because this is basically how guitar strings work. So you know, standing waves are literally what a guitar is doing when it's creating sound. Like you're sending standing waves down the string, they're vibrating and they're producing sound. You could also do this not with strings, but you could also do it with tubes or with pipes. And so that's how you can create like a pipe organ or a trombone or a flute. They're going to be creating standing waves that are going to resonate and get loud. So that's what's happening is if we look back at the animation again. So if you just focus on the amplitude of the resulting wave, you can see that the original waves were only this tall. Like they weren't as loud. They didn't have as much intensity, but the standing wave is going to be way louder. So we call this resonance. Like it's going to resonate like whoa, like it's going to get really loud. And so that's how you can make an instrument out of this is by sending those, making it the properties of the tube are such that it will resonate at these frequencies that correspond to those musical notes. And so that's why when you play a trombone, as you lengthen the slide, you'll hear the frequency of the sound change as you're adjusting the parameters of the length of the tube. It's changing which notes are able to resonate within it and get loud, and so you'll hear them. Whereas the other ones don't get loud. In fact, they actually cancel out with each other and get quiet. So all you're doing is you're just blowing into the end like, and you're just vibrating this column of air. And the only vibrations that can resonate and stay within it and get louder are the ones that match up with the length of the tube. So standing waves can be created within pipes. They can have open or closed ends. So just for some terminology, this is called an open end, and then this is called a closed end. And so waves will actually reflect off the ends, and the ends, they actually act like boundaries. So when the wave, like you have this pressure wave that's coming in here like a compression, when it reaches the end of the pipe, it'll actually reflect off the open end out there. And so whether it's an open or a closed end, like it makes sense that like you would reflect off a closed end, but it's kind of weird to think that you'd reflect off an open end. And it's really complicated physics on how that works. Like there's kind of like a partial vacuum that gets created and it ends up like sucking the particles back in once they try to leave. It's really complicated. It's beyond the scope of what we want to be discussing here. But just know that you can create resonance. Like the wave will come in here, hit one end, bounce off, come back, bounce off, come back, and you'll be able to create standing waves in here whether it's open or closed. Okay, here's an animation of a standing wave, longitudinal sound wave in a pipe. So we can see that over here. We have an oscillator that's driving this column of air into motion, and then it looks like the particle, like it looks like the wave isn't going anywhere. Like these particles are just like hanging out doing nothing. But really, if you looked at the displacement of each particle and graphed that displacement with the position, you'd get what looks like a standing wave. Or if you graph the pressure, you get what looks like a standing wave as we've been representing them. All right, so which end of the pipe is a node and which end of the pipe is an antinode? So we'll notice that, I should not have closed that. So the end of the pipe that's a node is the end where it looks like it's fixed. So like the particles are stuck in place and they're not going anywhere. So we can see that there appears to be a node here. There appears to be a node here. And then this end of the pipe is also a node. See, these particles aren't going anywhere. So the closed end of the pipe is a node. And then the antinode would be the open end of the pipe. So the pipe can act just like a string. The only difference is that we have to treat it as it can't be nodes on either end. It can't be fixed on both ends, if only if it's a closed tube. But that would be not realistic. But you're gonna have like a anyway. So it's gonna correspond to the string example that we just did. All right, so what we know is that for a pipe that's open, we're going to have an antinode at both ends, which means that the node is going to actually be in the center. So if I draw this picture, it's going to look like this. Next one, again, we have to have an antinode on both ends, and then that means that we're going to have a node, then an antinode, then a node. And so I'm going to try to draw this. Oh, I missed. Looks like that. And then that same pattern will just continue. So now we're going to have an antinode, node, antinode, node, antinode, node, antinode. Okay, here goes. Oh my gosh, this is so hard to draw. These are a pain in the butt. Okay, there we go. I'm not going to do these perfectly. And then I'll try to do one more. So it's going to be antinode, node, antinode, node, antinode, node, antinode, node, antinode. Did I do that right? 1, 2, 3, 4 antinodes. 1, 2, 3, 4, 5 antinodes. There we go. I missed. Try this one more time. Node, antinode, node, antinode, node, antinode. All right, close enough. Okay, so now we're going to find the wavelengths again. So looking up here, this is really weird because the length of the tube, once again, the full length of this thing is going to be L. And now if we look at our wave here, we're not even close to having a full wavelength for this first guy here. From the antinode to an antinode, we're nowhere near. So if we continue, let's see. So if we keep going to there. Okay, now I've got a full wavelength. So realize that from an antinode to an antinode, like this, from a crest to a trough, that's only half a wavelength. So once again, we have the same situation where lambda 1, so the first harmonic, the wavelength of the first harmonic is again is double the length of the pipe. For the second one, here to there, that's the full. So lambda 2 is equal to L. We have a full wavelength of the wave within this distance L. The next one, it's the same thing as before. The equations look exactly the same. So this is going to be, if we divide up the pipe into thirds, so there's 1/3, there's 2/3, there's 3/3. So once again, our wavelength is 2/3 of the pipe length. And then this one is the same as before, it's half. So we already know the general expression for this. Just like before, the wavelength of the nth harmonic will be 2L over n. And we can just check to make sure that that works. So if n is 1, 2L over 1 is 2L. If n is 2, 2L over 2 is L. If n is 3, 2L over 3 is 2/3 L. And if n is 4, 2L over 4 is 1/2 L. So same thing as before. There we go. Yeah, that's what I wanted. Okay, so what we realize is that this tube, open, is very similar to the string that was fixed on both ends. But what if the tube is closed on one end and open on the other? Looks like I'm way over time here. I'm going to keep going. If you guys want to stop, you can stop, but I got a little hiccup with the tech there, so I'm going to keep going for another 5 minutes. All right, so now let's check this out. So this one's really strange. So what has to happen here is we have to have an antinode. I'm sorry, I said that backwards. We have to have a node at the side that's closed, just like we saw in the animation up here. So if we watch this one more time. So the side that was closed, come on, this side of the tube is closed. You have to have a node there. See how the particles are fixed? We have to have a node there. Whereas the other side is free to move. So we're going to have an antinode over here. The way to draw that is that, well, it's node antinode. Like we don't have a repeating pattern here. Like there's nothing else in the middle. It's just going to go node straight to antinode like that. And if you look at this thing, what's the wavelength of the wave that's fitting in there? So I'm going from the 0 to the crest, back to the 0, to the trough, back to the 0 again. And so realize that that distance there is only, whoop, I didn't draw that very well. That's 1/4 the wavelength. So the full wavelength of the wave is actually 4 times the length of the pipe, or this full length here is L. Okay, if we look at the next one, we'll have node, antinode, node, but we can't have a node here. That can't happen. And so it's going to be node, antinode, node, antinode. And what will end up happening is we'll end up skipping one of the possible harmonics. Like it can't actually form. Since this side always has to be a node, we end up actually going to the third harmonic instead. So it's a weird thing that happens. So I'll go ahead and draw this. I'm going to go node, antinode, node, antinode. So it looks like this. And now we'll try to relate this. So we've got, let's see, so here to there to there. Okay, so we want to figure out how many, the full wavelength of the wave is how many L's. So if I kept going a little bit further to there, I would have finished the full wavelength. So now we'll divide this up into chunks. There, so there's 1 chunk, there's 2 chunks, there's 3 chunks, there's 4 chunks. So we can see that the full wavelength of the wave is how many chunks of L. So the full wavelength of the wave is how many L's. So we've got a full L plus an extra third of an L. So that's 4 thirds L. Did I do that right? I don't know if that's right. I think that seems correct, but it's kind of looking really, really weird to me right now. I'm going to check my notes real quick. See if I did that right. Yeah, that's what I got. Okay, cool. Okay, so then the next one, we're going to go node, antinode, node, antinode, node, antinode. So node, antinode, node, antinode, node, antinode. And now we'll look for where our full wavelength is. It's right there. And then we'll break it up into chunks. So let's see. And this is really weird. Okay, there is a chunk. I'll just do it like this. I think that makes the most sense. Okay, so to get to the full wavelength, we need to grab 1 of these, 2 of these, 3 of these, 4 of these. Now, how much are each of those? There's 1, 2, 3, 4, 5 of them in an L, and so we need 4/5 of them. So we'll just chunk up the pipe every time there's a node or an antinode. We'll call that like 1 fraction of the pipe, and then we just counted up that the full wavelength required 4 of those fractions. We'll do the last one. This is going to be gross. N-A-N-A-N-A-N-A. Okay, here it goes. And we'll do the same thing as before. Break the pipe into these chunks. Oh, I missed really bad. Okay, and then we're going to look for where our full wavelength is. So it's from here to there. And so how many of those chunks did we have to get? We took 4. And now how many are there total? There's 1, 2, 3, 4, 5, 6, 7 total. So we took 4/7 of L. And then we can start to see, oh, I did these wrong. Remember, it skips. So that's why that you can see how it's skipping here, because the generic expression is going to be, so the generic wavelength, the nth wavelength is going to be 4L over N, but we have to skip on the N's. So for example, if you try to do N equals to 2, it won't work. But if we do N equals to 3, it does work. You just get 4L over 3. If we do N equals to 5, 4L over 5. And so we're skipping the even harmonics. They cannot form in this tube. Only the odd harmonics can form. So that's our general expression for the nth harmonic. Okay, so that's basically what you need to remember is it's just 2L over N, except if it's an open close and it's 4L over N. All right, there are some worked examples. I'm going to solve these. I know my video is way over time right now, but I am going to go ahead and solve these just if you guys decide that you will. If you want to, I'm going to post questions on the Google Classroom. You may need to see these for practice. If you feel like, I don't need to see practice questions, just go figure it out on your own. You can just go ahead and figure it out on your own. But I'm going to keep going here. Okay, standing wave set up on a string with both ends fixed. The frequency of the first harmonic is 150 hertz, and it wants us to calculate the length of the string and the wavelength of the sound produced. And it says that the wave speed is 240 meters per second, and the speed of sound in air is 340 meters per second. Okay, so the first thing we know is that the frequency, what was it? Oh yeah, the wavelength of the nth harmonic, this is a string with both ends fixed, is going to be 2L over N. That's our wavelength of the nth harmonic with both ends fixed. So remember that the string both ends fixed is the same as the tube both ends open. It's the same relationship. It's 2L over N. We can go back up and show that. This is up here. So it's 2L over N. So that's where I'm getting that from. That's just what you remember. You just remember that. Okay, so it says the first harmonic is 150 hertz. So if we go here and plug in an N, then we get that the first harmonic is 2L over N, which is just 1. So the first harmonic is 2L, but it's giving us the frequency of 150 hertz. We have to remember that C is equal to lambda F. So that means that lambda is C over F. And so now we can substitute that into here. So C over F equals to 2L. This is for the first harmonic. And so we know that the first harmonic is 150, and we know the wave speed is 240. And so now we can find the length of the string. So that means that the length of the string L is going to be equal to C over 2F, where C is the speed of the wave on the string, which is 240, and then 2 times the fundamental frequency, which is 150. And so if you do this math, it's going to be, let's see. I'll just grab a calculator. I don't feel like figuring it. It's 240 over 300. So let me grab a calculator. So I'll just put 240 over 300, and I get 0.8 meters. And it looks like we have 2 sig figs, so it's probably better to express this as 0.80 meters. So that's the length of the string. Next, we want to figure out the wavelength of the sound produced. So now realize that the string is going to be oscillating. Whoops. The string will be vibrating. Come on, eraser. Oh, jeez. There. The string is going to be oscillating with that frequency of 150 hertz. And the string has this length, 0.8 meters. But the sound is not going to be moving at the same rate that the string is. The sound will be produced at the same frequency, like you'll be pushing against the sound, the air, and creating that sound. But the sound is going to travel a lot faster. So that means that the wavelength of the sound is not going to be the same as the wavelength of our string. They're going to be different. So if we want to find the wavelength of the sound, so we're going to have to, so I'll do it down here. So the wavelength of the sound. So we'll do the same thing. So wavelength is going to be equal to C over F. We know what the speed of sound is 340. And we know what our frequency is 150. And so this gives us a wavelength in sound, in air for the sound of 2.3 meters. Whereas the wavelength of the string was 1.6 meters. So that you can see up here, if we actually, now that we know that L was 0.8, you double that, you get 1.6 meters. So the wavelength of the string wave was 1.6 meters, whereas the wavelength of the sound wave was 2.3 meters. The reason the wavelength was longer is because the sound was traveling faster. The speed of sound was faster than the speed of the wave string, the string wave. I don't know what to call it. Okay, last one, it says a pipe has one end open and one end closed. Determine the ratio of the frequency of the first harmonic to that of the next harmonic. So we'll have one end open and one end closed. It wants us to find the ratio of the first to the next. Okay, so this is the frequency. So what we know is we know that the wavelength of the first one is going to be 4L over 1. And the wavelength of the next one, well, that one doesn't exist. But the third one does exist. Let me just leave that one off. So we want to find the wavelength of the third one, which is going to be 4L over 3. and we want to find the ratio of the frequency. Well, this is the wavelength, but we can turn this into a frequency by just doing C over F. Just notice how crooked I'm writing. It's funny. Okay, so what we're going to do is take the ratio of the frequencies. So solving this for F1, I'll try to write not crooked now. So solving this for F1, I'm going to get C over 4L. And solving this for F3, I'm going to get 3C over 4L. And so now I just want to find the ratio of these two things. And so that means literally just dividing these two guys by each other. So C over 4L over 3C over 4L. So the L's are going to cancel out. The 4 is going to cancel out. The C's are going to cancel out. And I'm just going to be left with 1 over 3. That's the answer. All right, that's it. Sorry this video went so long. Apologize for all the stream issues and man, not a good morning. But anyway, I'll see you guys later. Have a good day.